need to know some vocabulary in order to understand what it's asking us here. Regression lines are extremely useful when we're trying to forecast some kind of data set. And it's highly discussed in the fields of statistics. It's used to describe the relationship, if any, between a dependent variable and one or more independent variables. And if anyone is likes statistics at all, I highly recommend taking a statistics class. It can be very valuable in all of your fields of study, no matter what field of study you intend to go into, to better understand data in the world around us. Our goal today is to find a line which is close to all our data points, even though it may not go through all of the data points, or any for that matter. And that's going to be called the line of best fit. Today, we're going to focus our line of best fit using linear and quadratic. So whether it's going to be a nice straight line, or if we're going to be looking at a quadratic line to help us. This line of best fit is called the least squares regression line. So we can utilize the line of best fit. In our homework, it's going to ask you for what is the least squares regression line. And so that's your key to find the equation for either a linear or quadratic. Now, when we start graphing in Desmos, we're going to have to be very careful about whether we're using the little r or the big R. And so when I'm looking at a linear line, I'm looking for the little r. When it's close to 1, it's a linear fit. When big R squared is close to 1, it is a better quadratic fit. So little r is for a linear line, and big R squared is for a quadratic. And we will see what they look like and where we find them in Desmos. We do have little r squared, so don't get little r squared confused with big R squared. Little r squared is what we call the coefficient of determination. It's to help determine the extent of how one variable is affecting the second variable. Highly talked about in statistics. I'm letting you know that that's what it means when we see it. We're just not going to tackle it in our class because we need to know a little bit more about statistics and their effects on one another before we can go there. So, but just know that little r squared is there, but we're looking for little r and big R squared in our notes. And unless otherwise noted, round to 3 decimal places for accuracy. So our first problem here is using the energy consumption in the United States over the past 50 years is contained in the following table. Plot the data using a graphing calculator. I'm going to show you how to plot this and do things in Desmos. However, if you would like to use your TI, your Texas Instrument Calculator, page 226 in our digital textbook shows you how to do that. And if anyone is planning on using their TI calculator, also let me know. I can also provide assistance showing you what that looks like. I just find Desmos to be much more user-friendly in that manner. So I'm going to move on to slide 3. How did I get this table? How did I get these numbers before we answer the question? So let's start off by just plotting in Desmos. So in Desmos, there's a plus sign on the top left, and I'm going to click that Add Item button and then select Table. In my table, I'm going to put in my X values just as they're stated, 1950 through 2000. You'll see it kind of auto gets the idea and auto advances for us. And then on my Y values, I'm going to put in, this is the energy consumed in quadrillions. All right. Now I notice that I don't see my graph on the right-hand side, my numbers. So I'm going to, in the top right-hand side, click Graph Settings, and I'm going to change my X values. I'm going to maybe start my X values, maybe 1940 and go till 2010. And I'm going to change my Y values, maybe start at, I don't know, 0 and go to 120, just to kind of get an idea. I see now my dots popped up, and maybe just zoom out just one with that negative, just zoom out just one click so I can see kind of a better view of them. All right, now in my second line, we need to find the line of best fit. Perhaps a linear line might fit this. Our points are going up and to the right in a positive linear direction. And so how do I get that y sub 1 is about equal to mx sub 1 plus b is what we're going to do. So I need to utilize my little keypad down in the bottom left to help me. I'm also going to need to click the little ABC button so that I can get the sub value. So I'm going to start off by typing y and then looking for that little a sub b, which is right next to 1, 2, 3. So I can put the little 1 value. Why do I need to have that 1? Well, it's telling decimals where I'm pulling the information from. So I'm pulling my y values from the table, and in my table, my y values are y sub 1. So I'm just using the y values from this table, because it is very possible that if you're working in decimals, you can have multiple tables of data. So it's just telling me where to pull that data from. And then I need to put this tilde, this little about sign, which is to the right, and then mx plus b. So I'm going to start by typing mx, but I also need to say I want to grab my x values from the table. So x sub 1 using that a little b. And then I'm going to type in plus b. So the information that we see on our table here now matches what we have in Jamboard. So I'm going to move over to Jamboard, since now we know how I found that information so that we can help interpret it. So I would say part 2, find the least squares regression and comment on the goodness of fit. So notice I need my r, because r, little r, is associated with a linear line. I see my little r is pretty close to 1. And since it's pretty close to 1, I mean, it's not very far away from it, I would say this is a good fit. Now it's asking for the least squares regression line. Well, now that I know that the linear line is appropriate, notice it gives me my m and my b values. Thus, my equation is y equals my m value, 1.287, times x plus b. Well, in this case, our b is negative, so negative 2,473.89. Interpret the slope. What is the slope? Let's interpret our slope here. Well, we know that slope is the change in y values over our change in x values. Well, what was changing in our y values? The change in y values was, in fact, the energy use, right? It was the energy use in quadrillions, I believe it was. Yep, energy use in quadrillions. And then the change in our x values was the years. And since our slope is positive, we could say, and it's 1.287, we could say that our energy use increases $1.287 quadrillion. And since we don't have a nice fraction, it's a decimal, we know that this decimal is all over 1, so per year. This follow-up question is to use the regression line that we just had to predict the U.S. energy consumption in 2013. Well, notice in my table, we were using the exact years themselves. We weren't using a value such as a year since 1950 or something like that. So be careful how it's interpreted. We use the exact years themselves, and I'm looking for 2013 here. What was the consumption that we utilized? So my x value is 2013. We need to find what the y value is that matches that. Well, you could certainly put this in a table and determine this, or we could substitute our value in. So y is 1.287 times 2013, our x value, minus 2,473.89, which I know you all know how to operate a calculator. So we'll get approximately 116.841 quadrillion. This seems to be in line, right? 2013 is larger than 2000. And we are noticing that we are certainly increasing. So this seems reasonable with our table of values of the data that we do have. Now use the regression line to go backwards and predict when is the annual consumption. What is our consumption? Oops. What is our consumption? We'll reach 120, when? Oh geez, I had it all. Ooh. We'll try that again. Predict the annual consumption. So what is the year in which we will reach 120 quadrillion? There we go. Words are hard today, I guess. So I know my y value is 120. I now need to solve for x, which I know all of you can do. And I'll let you solve for x, but x should be approximately 2015.45. So about the year 2015, which makes sense, right? 2015, when we would reach 120 quadrillion, makes sense within our table. Trying another one here. According to the National Weather Service, the predicted hourly temperature for Paynesville on March 3rd, 2009 was given by the table below. Now, I'm going to warn us here. If I think about plotting these points, and let's let x be our time and y be our temperature, notice that 10 a.m. would be to the right, and then 1 p.m. is actually after 10 a.m. But if I were to plot this, it would actually put the 1 p.m. to the left, right? Because your graph, your x and y table, your x values aren't understanding a.m. and p.m. So you might want to consider when using time to use military time or the 24-hour clock. So that 1 p.m. actually represents the hour 13, 2 p.m. is the hour 14, 3 p.m. is 15, and 4 p.m. is 16 using the 24-hour clock. So then it will plot your points just as we had anticipated them to do. So I'm going to go back over to Desmos, and I'm going to reset my chart here. So at 10 a.m. it was 17 degrees. At 11 a.m. it was 19. At 12 p.m. it was 21. At 1 p.m. it was 23 degrees. At 2 p.m. or 14 it was 24. At 3 p.m. or 15 it was also 24. And at 4 p.m. or 16 it was 23. So notice as I was redoing that chart, our y equals mx plus b constantly was changing here. And then I'm also going to reset to go back home here and reposition my graph. So let's just let our x values go from there to, let's say, 24 hours. And our y values, let's have our y values go from 0 to 30. There we are. That looks a little better. Well, now as I look at my statistics here, my 0.8861 for my R value is not bad, but maybe a quadratic might fit better. So I'm also in line 3 going to add the quadratic general form so that I can understand those statistics. I need my big R squared to see which one might be a better fit. Also, as I notice my points, there are kind of curvy. There looks like there could be a vertex there at the very tippy top at 24. So let's see if we could put that in there. So I'm still going to need y sub 1, so I can pull my data from my chart itself. So y ABC sub 1 is about equal to, now the general form of the quadratic form is ax squared plus bx plus c. So I still need to put that here. So I still need ax sub 1, but I also need to square x. So I'm going to move my cursor back to the x, right next to the x. And then in my 1, 2, 3, I can square it. So ax squared. So the sub 1 is still there. So I know I'm pulling my x values from my table. Plus bx, also sub 1, plus c. And now I see that it gives me a new linear regression line that's quadratic. This one seems to fit our points a little bit better, if I do say so myself. So in my notes then, in Jamboard, I've got all of these same pieces already copied over for us. So we plotted the points using a graphing calculator. So then slide 6, let's do something with that data. Find the least square regression and comment on the goodness of fit. Okay, so let's look. We're looking at little r for linear, and I'm looking at big R squared for quadratic. When I compare the two, notice that big R squared is closer to 1. So a quadratic fit is much more reasonable. So I'm going to say that the quadratic regression is a better fit. Because R squared is closer to 1. So then what is that least squares regression line? What is that equation? Notice these parameters. It gives us what our A, our B, and our C values need to be. Thus, our equation is y equals ax squared, so negative 0.321 rounded to 3 decimal places, x squared, plus bx, 9.464 x, plus c, in our case it was negative, so minus 45.857. Use our regression line to predict the warmest temperature and when that time of day will be. So if we're the warmest, if we're thinking that our y values are representing the temperature, the highest point is going to be our vertex. Where our vertex is given by x and y, so our x value gives us the time, and our y value gives us the temperature. So remember, negative b over 2a, and then our function evaluated at negative b over 2a gives us the vertex itself. And we already know what b and a are from the parameters. So let's try it out. So negative b, so negative 9.464 over 2 times our a value, negative 0.321. You guys work your magic with your calculators. This gives us 14.741. And now I can evaluate wherever I see x. I'll let you plug that into your calculator. We're going to substitute in 14.741, and you should get 23.899. Well, 14, recall, we put our answers in, our x values in using the 24-hour clock. So 14.74 is in between here. Remember, 14 was a 2 p.m. and 15 is 3 p.m. So when will our warmest temperature occur using the regression line? Between 2 p.m. and 3 p.m., the temp will be about 23.899. Now you may be thinking, but Harmony, it says here that our warmest temperature was 24. Again, this is using a regression line to estimate what fits our points the best. It's not always going to go through every single point that we have on our line itself. So just be aware of that. Okay. Our next one is a dog's lifespan is typically much shorter than that of a human. The age equivalency for dogs and humans are listed in the following table. So instead of wasting time going through and entering the table, I'll let you go ahead and do that. Now that you know, now that we have the table set up, you can go back and edit your table. Once these line 2 and line 3 are set up, you can edit your table as often and add as many rows as you need. So you could certainly bring it up once, fill it out, and then just change the values on your table, and then it'll automatically change your linear and quadratic regression lines below, which is kind of a cool feature. So once you go ahead and do that, then let's look at the information that's given. So which function model provides the best fit for the data that's provided? How do you know? So this was our linear line, and as a reminder, our linear line, we're looking at little r, but our quadratic line, we look at big R squared. Ooh, they are so close to each other. They're so close. So they're both actually really great, both representational of this. So we certainly could use either or. However, when I'm looking at the thousands place, the linear line is just ever so slightly better for us. So I'm going to say that we're going to use the linear line, linear regression, as it is closer to 1. So what is our equation then? Again, we look at our parameters. They already give us those parameters for our linear line. Y equals our m value, 4.401 when rounded, plus b, 11.095. Using the function from part 3, estimate the equivalent human age for dogs that are 5, 11, and 15. So when we look back here at our previous slide, dogs were our X values and humans were the Y values. So dogs were X, human is Y. We are given a dog's age value. So we are given the X value, we need to find the Y value. And notice I did a little chart here. So I want to show you how I entered in this chart to make life a little easier for calculating. So to do that, I'm just going to start a new line here. I'm going to enter in my regression line. We said our regression was y is 4.401x plus 11.095. Then while I'm highlighted here, notice I'm going to grab this little gear right at the top. It says edit list. When I select this option, it's going to let me turn in that equation into a table. So I'm going to turn that into a table. And notice I can select any value for X. Recall X is the dog age years, and Y, or once we substitute that in, will give us the human years. So our dogs' ages were 5, 11, and 15. You could get rid of all these if you wanted. We don't care about them. Or just randomly put numbers in there if you decide. We're just curious about here. So when the dog's age is 5, the human years then is 33.1, or simply taking 5 and substituting it in for X and using our calculator. This is just a great way. The downfall of using the table feature here, as we go back, is that we are able to substitute X in to give us the Y, but we can't go backwards. So I can't put a value in here, a human age of 40, and find out what the dog year is. The table doesn't go backwards in decimals. So it only allows us to input X values to find the output, but you will have to use algebra to, let's say, find Y if X, find X if Y is, let's say, 40 as an example, human years, in order to find the dog years, we would need to use algebra in order to get X by itself. So that's just kind of a downfall, but using the table feature could certainly save you some time as well. And that, my friends, is the end of 2.5.